Hey guys, so with this video we will start our next unit on circular motion. This type of motion occurs a lot in the world around us. It occurs when you turn the corner, or turn the corner in the road in your car, when you're on a roller coaster. It also will apply to the motion of the planets and the motion of stars and galaxies. So learning about this helps you kind of view the universe and appreciate the universe and how it works in a fuller and deeper way, which is why I kind of like it. Now, one of the things about circular motion, which will be different than the motion that we've studied so far, is that in circular motion, the direction of the acceleration keeps on changing. So all the motion that we've studied up to this point, the acceleration was always pointing in the same direction the entire time, whether it was in free fall, throwing a ball up in the air, whether it was moving along the ground, or whether it was in the case of projectile motion again, kind of a special type of free fall where the acceleration was always pointing down. In circular motion, what we'll find is that the acceleration keeps on changing direction. And so when we look at a object moving in a circle, so this dotted line here might be a circular path, and I'll have an object, it's moving in a circle, its velocity will always be tangent to the path. Okay, very often this is called our tangential velocity. Okay, so tangential velocity. Okay, so as it goes from here, let's call this V initial. So this little I stands for initial. And then maybe it moves to right here. And again, that's going to be tangent to the circle. You can call that VF. And we want to know the direction of the acceleration. So in this case, what's happening with the acceleration, it's not that the magnitude of the velocity is changing, it's that its direction is changing. Remember, when we talk about acceleration, this acceleration, the way we defined it, is it's just the change in velocity over the change in time. And there's two ways that I can change that velocity. One way, what we've been doing up until now, is changing the magnitude or changing the speed. But we can also change velocity by changing the direction of that velocity. And so if we add these together like vectors, so when we talked about vectors, we said how we can take vectors and we can add or subtract them from each other. When we do this, we have to arrange things head to tail. And so I'm going to do it with these two vectors. I'm going to say, okay, so VF is pointing down this way. And VI originally was pointing off to the right, but I'm going to have a negative VI here. So when we take the negative of a vector, we change the direction. So this will be negative VI. Okay, so if I take the negative of this, just flip the vector around. And what I get, let's see if I can change colors here. What I get, the resultant of this starts from the tail, goes to the head, goes in this direction, which means that the change in this velocity over time points in this direction. And that's the direction of the change in velocity. And this is also the direction of my acceleration. So I'm going to put a little c as a subscript here. I'm going to call this a sub c. And this is what's called the centripetal acceleration. Okay, so that's the term we use for this. It's called centripetal because centripetal means center seeking. Okay, so center seeking. So this is always going to point towards the center. The acceleration throughout this whole time is always going to point towards the center of the circular path. Okay. All right, so that's centripetal acceleration. And as we learned with the second law, if we have an acceleration, then we also need to have a force. Okay, so just as we can have a centripetal acceleration, what happens is there has to be some force that causes this acceleration. Okay, and that force is also going to point towards the center. So F sub c, centripetal force, is going to point towards the center of the circle. Now, here is the point where a lot of students tend to get confused because they think that the centripetal force is some new or different type of force. And so I want to make it clear to you guys that centripetal force is actually caused by one of the forces we've studied already. Okay, so let me give you a brief list here, although this won't be exhaustive, so this isn't going to include everything. So forces that can act as centripetal forces. So centripetal, again, just means pointing towards the center. So if there's a force that acts on an object that is moving in a circle and that force points towards the center, then we call it a centripetal force. Okay, so things that can do this. Gravity, the force of gravity is a big one. So the force of gravity acting on the Earth acts as the centripetal force, and it keeps the Earth in orbit around the sun. Something else could be the tension in a string. Okay, so if you have, like a ball tied to a string and it's being twirled around in a circle, then this tension is my centripetal force. Okay. Something else, and this occurs on roadways. So as your car is making a turn, what's happening is friction between the tires and the road. Kind of push the car towards the center of the circular path. So you imagine if you're making a turn here, it's kind of like a part of a circle at the center right there. And so friction will keep on pushing your car towards the center and allow you to make that turn. And we know this because if the road's icy and that friction doesn't exist, your car will go straight. Okay. So the centripetal force, it's not a new type of force. It's not like friction or gravity or tension. It's not like we have friction, gravity, tension, and then some centripetal force. One of these forces will act towards the center, and so we call it a centripetal force because of the direction it's pointing in, not because it's a new type of force. I hope that's clear to you guys, and I'll keep on emphasizing it in class. So we have centripetal acceleration, we have centripetal force, and it turns out there's certain equations that we can use to calculate both of these. So for centripetal acceleration, E sub c, that's going to be equal to the velocity squared divided by the radius of the circle. Okay, so this is my tangential velocity. Okay, tangential velocity. Okay, make sure yeah, so that's this velocity right here, how fast in meters per second it's moving around the circle. Okay, so this can be the tangential velocity in meters per second squared, don't forget to square it, divided by the radius of the circle. Okay, of that circular path that we're following in meters. So this equation is for centripetal acceleration. And then, since we know that force, the net force, is equal to ma, we can say that the net force that acts towards the center of the circle is equal to m times the centripetal acceleration. So it'll be mv squared over r. Okay, where m is the mass of the object that's moving in a circle. Moving in circle. That's in kilograms. Okay, so this equation right here and this equation right here we'll be using in our problem solving. We will definitely practice problems involving both of these in class and talk about the concepts a little bit more. If you guys have any questions, please write them down in your notes and let me know.